Hello, this tutorial is on significant figures, and I think it's applicable for many students who are majoring in natural sciences subjects such as physics, biology, chemistry, and even mathematics. When we talk about significant figures, I first want to address that there are two types of numbers, exact and approximate. So for instance, if I were to give an example of an exact number, I can say in my statement that I have 40 students in my class. That is an exact number. Approximate, though, is a little bit different, and it tends to be more aligned with regard to taking measurements. When we take measurements, the accuracy of that number or of that approximation is pretty much determined by the precision of the instrument. So significant figures are really important, and students sometimes have difficulty in determining the significance of a number and being able to justify the accuracy of a measurement. We need to learn about significant figures, especially when we want to report experimental data. So for instance, in this example, if my experiment requires me to use a measuring rule, and I measure a line segment to be 2.1 centimeters, it is not accurate for me to state that the length of the line is 2.10 centimeters because I am specifying a greater accuracy than what is justified. For the vernier caliper now, if I have a measurement of 3.42 centimeters, this measurement has three significant figures. To imply that if I were to have a measurement of 3.420 centimeters is not correct, because again, I cannot justify this greater accuracy. To figure out and to learn about how to determine the number of significance or the number of significant figures, there are several rules that I think is pretty useful, and it will help us in determining the amount of significant figures in a number. The first one is pretty simple. It says all non-zero numbers are always significant. So as long as it's not a zero, we can count it as being significant. In this example, 916 has three significant figures. The second one, it says 73.36. I'm going to count all my non-zero numbers, so therefore there are four significant figures. 5.7 has two significant figures, and this number, 67.775, actually says that there will be five significant figures. In the second rule, it's saying all zeros between non-zero numbers are always significant. So for instance, if I have a zero in the middle of the number, then it is significant and I need to include it. So at this number, 94.072, I have a zero between non-zero numbers. So therefore, I do count it and include it. So in this case, it's five significant figures. In my example, I am counting five significant figures. Again, the zeros in the middle of a number are counted. 4009 has four significant figures. 705 has three. In the third rule, zeros at the beginning of a number are not significant. They pretty much act only to locate the decimal point. So in this number, 0.0834 centimeters, those two zeros at the beginning, they are not significant. So in this example, I am counting three significant figures. In 0.02907 milliliters, again, I do not count the two zeros at the beginning, but rule 2 tells me that I need to consider the zero in the middle. So 2907 actually has 4 significant figures. For my example, 0.05 has 1. Again, the 2 zeros in the beginning, they are not significant. 0.026 has 2. 0.0024 has 2. The fourth rule: zeros at the end of a number and after the decimal point, they are indeed considered to be significant. So it's assumed that we won't show these unless they were important. In this example, I have 138.200. The 0 at the end of a number and after the decimal point, they are considered significant, so therefore this number has 6 significant figures. If the value were known to only have 4, then I would represent it as 138.2. So for my example, 7.20 has 3 significant figures. 0.0023900, I do not count the first 3 zeros because they are at the beginning, but the zeros at the end are considered to be significant. So in this case, there will be 5 significant figures. In the fifth rule, zeros at the end of a number and before an implied decimal point may or may not be significant. We cannot really tell whether they are part of the measurement or whether we're just using it to locate the unwritten but implied decimal point. So if I were to give this number 8200, it's not really clear if the zeros are significant or not. We know that there are at least 2 significant numbers, but technically it could be 3 significant figures or even 4. To definitely say that this number has 4 significant figures, it should be written as 8200 decimal place. So you should put that decimal point. But as it is, since there is no decimal point stated at the end, we can justify that there's at least 2, but keep in mind that it can be 3 or 4. One thing that I noticed, and it's a really useful tool, especially in determining significant figures, is the use of scientific notation. So if you're unsure, always put your number in the scientific notation format. And this is to help to place significant zeros behind a decimal point. Very useful tool. Before I continue, I need to point out another subtopic, and this is involving rounding, and it helps with regard to justifying significant figures. There are 2 easy rules when it comes to rounding, or some people say rounding off. If the first digit you remove is 4 or less, you're going to drop it and all the following digits. But if the first digit removed is 5 or greater, you're going to round up by adding 1 to the last digit kept. So for the first example, if I have to look at the 2.4371, if I want it into 2 significant figures, I look at the 2, the 4, and the 3. So 2 significant figures is really 2.4. But to determine whether that 4 stays the same or if it goes up by 1, I look at the 3. The 3 is 5. Well, it's 4 or less. So therefore, I keep it as 2.4. I don't increase the 4 by 1. In the second example, if I have 4.5832 and I want to get it to 2 significant figures, I look at the 4, the 5, and the 8. The 8 is helping me to determine what I'm going to do with that 5. Since it is 5 or greater, then I need to round up by adding 1. So then it becomes 4.6. And that is to 2 significant figures. Another useful set of guidelines, or you can say rules, is when it comes to addition, multiplication, division, or even subtraction. With respect to adding or subtracting, when measurements are added or subtracted, the answer can contain no more decimal places than the least accurate measurement. So what does that mean? If I were to give you this math sum, well, this subtraction example, and it has 95.5, which is three significant figures, minus 7.343, which is four significant figures. But since this is a subtraction, I look at the guideline above and I need to look at the decimal places. So in my first number, 95.5, I have one decimal place. In the second number, I have three decimal places. So that means my final answer should have one decimal place, because again, it cannot contain no more decimal places than the least accurate measurement. In this case, the least accurate measurement is going to be the 95.5. So if I were to do this problem, my calculator is going to display 88.157. But my knowledge of significant figures and using the guideline, it tells me that I cannot be more accurate than my least accurate measurement. So in this case, I present it as 88.2. The reason why the 2 is there is because I look at the 5, it's greater, 5 or greater, so therefore I need to increase that number, 88.1, that 1, add 1, and that becomes 2. In the second example, I look at my least accurate measurement. That's a 17.4. It's telling me I only have one decimal place. So when I present my final answer, I have to be sure that it's only one decimal place. My calculator is going to display 19.893. But to get one decimal place, I present my number as 19.9. In this other example, I look for the least accurate measurement, and that pretty much is the 27.674, which has three decimal places, and the 4.673, which also has three decimal places. So therefore my final answer should have three decimal places. My calculator is going to display 37.2895, but to represent three decimal places, my number is really, or my final answer is really 37.290. Remember that 0 at the end is considered to be significant. When it comes to multiplication or division, we actually have to look at the number of significant figures, and our final answer can contain no more significant figures than the least accurate measurement. So with addition and subtraction, we're going to look at the decimal places, but when it comes to multiplication or division, we're going to count the number of significant figures. So for my example, 7.6 multiplied by 0.0024, the least accurate measurement actually is the 0.0024, because that has two significant figures. My calculator is going to display 0.018408, but my final answer should have two significant figures, which actually is 0.018. My next example, I'm going to look at the least accurate measurement, which actually is 4.26, which has three significant figures. So even though my calculator display 1.87887 by 10 to the 3, to present it into three significant figures, my final answer actually is 1,880. And lastly, 24 multiplied by 52, both numbers actually has two significant figures. My number, or my calculator, has displayed 1248. To get my number into the two significant figures, I'm going to use that tool of putting it into the format of scientific notation. That is going to help me to determine my final answer. 1.248 by 10 to the 3, I want two significant figures, so I'm going to look at the 1.2. The third number that I'm going to look at is the 4. It's less than 5, so I'm going to leave the 2 as is. So in scientific notation, I'm going to get 1.2 by 10 to the 3, and when I remove the scientific notation format, my answer is actually going to be 1200. And that is indeed, I can justify and say that there are at least two significant figures in that number. Lastly, let's look at this simple example, and it sort of summarizes what we have learned about significant figures. If I were to ask you to divide the following and report your answer to the correct number of significant figures, I have 0.530. The numerator has 3 significant figures. The denominator actually has 4 significant figures, but I go back to my guideline where my final answer should contain no more significant figures than the least accurate measurement, which is my numerator. My calculator is going to display this number, but I know that I need to have 3 significant figures, so it's going to be 5.25. That 4 got rounded up because the 7 is 5 or greater.